10.2 Infinite Series. The outline of this video is as follows. We will begin by introducing the core concept of an infinite series, which is the process of adding up an endless sequence of numbers. Next, we will explore how to determine if such an infinite sum has a finite value. This involves the critical ideas of partial sums and the formal definition of convergence. Following that, we will focus on a special, but very common, type of series known as a geometric series, and learn a straightforward test to determine if it converges and what its sum is. We will then cover our first major diagnostic tool, the nth term test, which helps us quickly identify series that diverge. Finally, we will establish some algebraic rules for combining series, which will allow us to break down more complex problems into simpler parts. Now that we understand sequences, we can ask a new question. What does it mean to add up all the terms of an infinite sequence? This sum is called an infinite series, and we need a special tool to define its value. Since we cannot perform an infinite number of additions, we instead create a new sequence called the sequence of partial sums. The nth partial sum, which we call S sub n, is simply the sum of the first n terms of the series. We then analyze the limit of this new sequence of partial sums as n approaches infinity. If the sequence of partial sums converges to a finite number L, we say the series converges and its sum is equal to L. If the sequence of partial sums does not converge to a specific value, the series diverges and does not have a sum. Therefore, the convergence of a series is entirely determined by the convergence of its sequence of partial sums. Let us walk through a concrete example to see how we can find the sum of an infinite series. The central idea is to analyze the sequence of its partial sums. Our example series is 1 plus 1 over 2 plus 1 over 4 plus 1 over 8, and so on. The first partial sum, S sub 1, is just the first term, 1. The second partial sum, S sub 2, is 1 plus 1 over 2, which is 3 over 2. The third, S sub 3, is the sum of the first three terms, which equals 7 over 4. A pattern emerges from these sums, giving us a general formula for the nth partial sum. S sub n equals 2 minus the quantity 1 over 2 to the power of n minus 1. To find the sum of the infinite series, we take the limit of this sequence as n approaches infinity. As n becomes very large, the fraction approaches 0, so the limit is simply 2. Therefore, we say the series converges, and its sum is 2. This slide summarizes the most important result for geometric series. We have a simple test that tells us not only if the series converges, but also exactly what value it converges to. The crucial condition depends entirely on the common ratio, r. If the absolute value of r is less than 1, the series converges. This happens because each successive term gets smaller, allowing the partial sums to approach a specific, finite value. For such a convergent series, the sum is given by a very useful formula, the first term, a, divided by the quantity 1 minus r. On the other hand, if the absolute value of r is greater than or equal to 1, the terms do not shrink towards 0, and the series diverges. In this case, the sum either grows without bound or oscillates, and it does not approach a finite limit. So the key takeaway is this. For any geometric series, its convergence is determined completely by the magnitude of its common ratio. Another practical application of the geometric series formula is converting any repeating decimal into an exact fraction. Let us examine the number 5.232323, and so on. We can separate this into two parts: the integer part, which is 5, and the repeating decimal part. This repeating part can be expressed as an infinite sum, 23 over 100 plus 23 over 100 squared plus 23 over 100 cubed, and so on. You can see that this sum is a geometric series. The first term, a, is 23 divided by 100. The common ratio, r, is 1 over 100. Since the absolute value of r is less than 1, the series converges. We can find its sum using the formula a divided by the quantity, 1 minus r. This gives us 23 over 99. Finally, we add this result back to the integer part we set aside at the beginning. The original number is therefore equal to 5 plus 23 over 99. Combining these into a single improper fraction gives us 518 over 99. Let us apply our knowledge of geometric series to a classic physics problem. Calculating the total distance traveled by a bouncing ball. We start by dropping a ball from an initial height, which we will call a. The total distance it travels is this first drop, plus the sum of all the subsequent ups and downs. After the first drop, the ball rebounds up a distance of a times r, and then falls that same distance down. The next rebound is up a times r squared, and then down that same amount. This pattern reveals that the total distance is the initial drop, a plus a geometric series. This series accounts for all the bounces, with a first term of 2ar and a common ratio of r. Because r is less than 1, this series converges to a finite sum. By adding the initial drop to the sum of this series, we can find the total distance traveled. The final result is that the total distance, s, equals a times the fraction 1 plus r over 1 minus r. Now let us look at a special type of series called a telescoping series, which is important because we can find its exact sum. A telescoping series is one where most of the terms in its partial sums cancel each other out, much like a collapsing telescope. Consider the example. The sum from n equals 1 to infinity of the fraction 1 over the quantity n times, n plus 1. The key is to first use partial fraction decomposition. This rewrites each term as 1 over n minus 1 over n plus 1. Next, let us examine the kth partial sum, s sub k. It is the sum of the first term, which is 1 minus 1/2, plus the second term, 1/2 minus 1/3, and so on. Notice how the negative part of each term cancels with the positive part of the next term. This cancellation leaves only the very first part, which is 1, and the very last part, which is -1 over the quantity, k plus 1. So the partial sum simplifies to just 1 minus 1 over k plus 1. To find the sum of the infinite series, we take the limit of this partial sum as k goes to infinity. The fraction 1 over k plus 1 goes to 0, so the series converges to 1. Let us formalize our first and simplest tool for analyzing series, the nth term test for divergence. This test provides a quick way to determine if a series cannot possibly converge. The core idea comes from what we just discussed. For any series to converge, its individual terms, a sub n, must approach 0 as n goes to infinity. The nth term test simply flips this logic around. It states that if the limit of the terms as n approaches infinity either fails to exist or is any number other than 0, then the series absolutely must diverge. However, it is crucial to understand the limitation of this test. It can only be used to prove that a series diverges. If you find that the limit of the terms does equal 0, this test tells you nothing at all. The series might converge, or it might still diverge. In that case, the test is inconclusive, and you must use a different method. So think of this as a preliminary check. If the terms do not approach 0, the series diverges. Let us apply the nth term test for divergence to a few more examples. The core idea is that for a series to converge, its individual terms must approach zero. If they do not, the series diverges. First, consider the series where each term is the fraction n plus 1 over n. As n becomes very large, this fraction approaches 1. Since the limit is not zero, the series diverges. Next, look at the series with terms -1 to the power of n plus 1. These terms alternate between +1 and -1 and never settle down. The limit does not exist, and therefore is not zero, so this series also diverges. Finally, for the series with terms -n over the quantity 2n plus 5, the limit as n approaches infinity is -1/2. In each of these cases, the limit of the terms is not zero, so the nth term test tells us that the series must diverge. This theorem provides powerful tools for working with series by showing that they follow familiar arithmetic rules. If you have two series that you already know are convergent, you can add or subtract them term by term, and the new series, sum, is simply the sum or difference of their individual sums. The same idea applies to multiplying a series by a constant. Let us apply this to the example on the slide. The initial series looks complicated, but we can algebraically split the fraction inside the summation into two parts. This transforms our one complicated series into the difference of two much simpler ones. Using the difference rule, we can now handle each one separately. Both of the resulting series are geometric series, which we know how to sum. The first one, with a ratio of 1/2, sums to 2. The second, with a ratio of 1/6, sums to the fraction 6 over 5. Subtracting the second sum from the first gives our final answer of 4 over 5. A quick word of caution: these rules only apply if the component series are convergent. The main takeaway is that we can break down complex convergent series into simpler, solvable parts. This slide covers two practical techniques for manipulating infinite series that help simplify our analysis. First, let us consider adding or deleting terms. The convergence of a series is determined by its tail, meaning the behavior of its terms as the index n goes to infinity. Therefore, adding or removing a finite number of terms at the beginning of a series will never change whether it converges or diverges. However, for a convergent series, this action will change its final sum. As the equation shows, the total sum is simply the sum of the initial terms plus the sum of the remaining infinite tails. Next, reindexing allows us to change the starting value of the index n without altering the series itself. This is a notational change, often done for convenience. For example, the geometric series shown can be written in several equivalent ways. Whether we start at n equals 1, n equals 0, or even n equals 5, we adjust the formula for the general term to ensure the sequence of terms being added remains identical. In summary, these two properties give us flexibility in how we write and analyze a series. Let us summarize the key ideas we have covered about infinite series. The fundamental definition of convergence is tied to the sequence of partial sums. A series converges to a sum L if, and only if, its sequence of partial sums converges to that same value L. We then focused on a special, powerful case, the geometric series. This series converges to the value a over the quantity 1 minus r, but only when the absolute value of the common ratio r is less than 1. We also established our first major test, the nth term test for divergence. This test states that if the terms of a series do not approach zero, the series must diverge. Remember the crucial caution here. If the terms do go to zero, the test is inconclusive. Finally, we saw that convergent series have useful algebraic properties, and that convergence is determined by the tail of the series, meaning a finite number of starting terms do not affect whether it converges or diverges. Let us wrap up by applying what we have learned to a couple of review questions. First, consider the series given by the sum from n equals 1 to infinity of the natural log of the fraction n over n plus 1. The question asks what the nth term test tells us about its convergence. To answer this, you will need to find the limit of the general term as n goes to infinity. The hint on the slide reminds you that the natural log of 1 is 0. Also consider the slide's title. Can you use the properties of logarithms to rewrite the term and see if the series is telescoping? The second question deals with a geometric series, the sum from n equals 0 to infinity of the quantity x minus 1 all over 2 raised to the power of n. For what values of x does this series converge? Recall that a geometric series converges if the absolute value of its common ratio is less than 1. Once you find the interval of convergence, use the formula for the sum of a geometric series to find its value. Take a moment to pause here and work through these problems. They are a great way to test your understanding of the key concepts we have covered.